Welcome to ninth lecture on adaptive signal processing course. In this video, we will continue our discussion on properties of autocorrelation matrix R, and this is the last part. Here I will give you few examples of capital R, and then we will discuss their properties. In previous lectures, total 8 properties of R we have discussed. First one, R is symmetrical. Second, R is Toeplitz. Third, R is non-negative definite matrix or positive semi-definite matrix, both are same. Fourth, eigenvalues of R are always non-negative and real. And fifth one, if Qi and Qj are two eigenvectors of capital R, and they are the eigenvectors for two distinct eigenvalues lambda I and lambda j, then Qi and Qj are orthogonal, means Qi transpose Qj will be 0. Sixth, if all the eigenvalues of capital R are distinct and corresponding eigenvectors, their norms are 1, means unit norm, then we can make one matrix Q, capital Q, where capital Q is the Q0, Q1, Q2 up to Ql minus 1. Means if we put those eigenvectors in column wise, one after another, then we will get this Q matrix, and that Q matrix is orthonormal. Means Q transpose Q equal to identity matrix, and Q transpose is also identity matrix. The seventh one, most important, that is the eigenvalue decomposition. We can decompose R in terms of the products of Q, capital lambda, Q transpose. Already we have defined the Q, and capital lambda is the diagonal matrix containing the eigenvalues of that corresponding eigenvectors. So lambda 0, lambda 1, lambda 2, lambda L minus 1. And last property we have discussed, that is the trace of R equals to sum of all eigenvalues. Right. Now I'll give you few examples of autocorrelation matrix R. First, we'll start with white input. And we know that if Xn is white input sequence, and if we consider expected value of Xn equals to 0, that implies that the mean value is 0, and expected value of X square n, if it is equals to sigma X square, that implies variance equals to sigma X square. And for this white input, the samples are not correlated at all. Means expected value of X of n minus m, so one delays X in a sequence, so n minus m that sample, and X of n minus L, where n not equal to L, if we consider, then these two are two different samples, and there is no correlation between two different samples, and that is equals to 0, okay, for m not equal to L. And when m equal to L, then it will become the square of that sample, means the variance sigma X square. So for this kind of white input, we have already discussed that this R matrix is of this form: expected value of Xn vector times X transpose n vector, right? So this is column vector, this is your row vector. If you multiply, you will get a matrix. So that expected value is your autocorrelation matrix capital R. So if you expand it, we'll get this kind of matrix. So in diagonal, you will see these are the expected value of x squared n minus 1 up to expected value of x squared n minus l plus 1. I have assumed that the signal this xn, so this autocorrelation matrix capital R of dimension L cross L, right? And xn vector will contain the sample xn minus 1, xn minus 2 up to x of n minus L plus 1. So here you can easily understand that these diagonal terms are always non-zero and its values are sigma x square. Okay, because it is wide sense stationary. So and other terms all are 0. So if I consider the 2 by 2 dimensional R matrix, then this first term will be sigma x square and next diagonal term sigma x square again, but these half diagonals they are zeros. So if you take sigma x square common, then we'll get this one, and this is nothing but identity matrix. So it is sigma x square times identity matrix. So in this case, the eigenvalues are very simple to calculate. Those are sigma x square both, and eigenvectors are basically standard basis vectors 1 0 and 0 1. Okay, because of this identity matrix. So as the eigenvectors are standard vectors, basis vectors, so there is no need for eigenvalue decomposition. So here already it is a diagonal matrix. Okay. Thus you will see that in adaptive signal processing, whenever we will consider white input, then it will be a little bit easy to analyze the adaptive algorithms. But this is not same for correlated input. Okay. So for 3 by 3, again, it's a simple extension. So these diagonals are sigma x square all, and off diagonals are zeros. So again, these all eigenvalues are same, sigma x square, and sigma x square. And eigenvectors are these standard basis vectors 1 0 0, 0 1 0, 0 0 1. Now we'll go for colored input. And we can generate this colored input from white input through some filtering process. Generally, we'll be using low-pass filter, and those low-pass filters we can design using FIR or IIR. So first we will consider one example for FIR filtering by which we can generate colored input from white input. So here, this is the filter coefficients, half and half, and UN is a white input sequence, and XN is the output sequence for this FIR filter. And here we'll assume that as UN is white, its mean is 0, variance is sigma u square, and there's no correlation between two different samples, that is 0. Now we'll try to understand the XN, properties of XN. So XN, you see, if this is your filter, then XN we can write, this is half times of UN, and this is your delay, half times of u of n minus 1. So we have discussed this kind of example previously, and if you have any doubt, I'll advise you to go through my previous lectures, then you can easily understand this operation. Now from this relation xn and un, if you take expected operator on both sides, easily we can say that expected value of xn will be 0 because its mean is 0, this mean is also 0. And expected value of x square n, if you take squared first and then if you take expected operator, then individually here you will get sigma u square by 4. For this square you will get sigma u square by 4, and cos term that will become vanish, because they are uncorrelated. Okay. So here you will see xn and xn minus L, so this matrix, this correlation, it will be sigma u square by 4 if and only if L equals to plus minus 1. Okay, and if this one is L equals to other than plus minus 1, then obviously this value x square n will be, this one expected value of xn minus L will be 0. Okay, but here you remember that L not equal to 0, it should be, because whenever L equal to 0, then you will get expected value of x square n, and that value is sigma u square n. Okay, so it implies that if we go for 2 by 2 matrix of R, then this two diagonal will be sigma u square by 2, because expected value of x square n is sigma u square by 2, and this is the adjacent only, thus this its correlation coefficient will be sigma u square by 4, this one as well as this one. Okay, so we can take sigma u square by 2 common, this will be 1, this is half, this is half, this is 1. Similarly for 3 by 3, so this diagonal all will contain the same value sigma u square by 2, and this diagonal sigma u square by 4, sigma u square 4, because they are adjacent. This is also sigma u square by 4, sigma u square by 4, but this one is 0, because this and this, first and third, there is no correlation. Okay, similarly this element is also 0. So we can extend this idea. Okay, this is your after simplification. So for this 4 by 4, easily we can see that, so the constant term here will be sigma square by 2, and here all will be 1. The next one will be all what? Half, because this is the correlation with the adjacent samples. This is half half, this is all half, and rest all are zeros. Okay, this is your 4 by 4 autocorrelation matrix. Now I'll consider the AR1 process, autoregressive system 1 process, by which we can also generate colored input. Now UN is as usual, it is a white input sequence, and this is autoregressive 1 process, and output sequence is xn, and the relation we have considered here, xn will depend on previous values of xn, means r times of x of n minus 1 plus un. Okay, so if you take z transform both sides, then x of z upon u of z will become 1 upon 1 minus r z to the power minus 1. So this system will contain no zeros, or okay, we can consider 1 0 at origin and 1 pole at r position. Okay, so this pole should be within unit circle, then the system is stable. And if it is on right side, it is a low pass filter, so we are considering one low pass filter. And for this system we have discussed previously in one lecture in detail, so you may go through that one. And for that we have obtained this one, the expected value of x square n is sigma u square upon 1 minus r square, and expected value of xn and xn minus or plus L, means the sample difference is L, then the correlation is same, similar thing is sigma u square upon 1 minus r square times r to the power L. So you see, as L is large, this value will decrease, because here we will consider that r is within 1 to minus 1. Okay, so as r is less than 1, so you see the r to the power L is decreasing exponentially. Okay. So for 2 by 2 matrix is very simple. So sigma is square upon 1 minus r square. So this is 1 1 and this is r, this is r. Okay, because this time L equal to 1 only, adjacent only. And for 3 by 3 I'll get this all here all 1, then this is all r, then this term is r squared and this term is r squared and this is r. Similarly we'll get 5 by 5. So you see sigma is squared by 1 minus r squared, it is common for all. This diagonal is all 1, next diagonal this all r, then r squared, then r cube, then r4, like that. Similarly this side r, this is r squared, this is r cube, this is r, and you know that this r is always 12 matrix. Okay. Now I'll consider this R1 AR1 process and pole at R position, and for that second order this 2 by 2 dimensional R is given by this one 1 1 RR, and sigma is square I have that part I have considered 1. Okay. We want to study this autocollision, this kind of autocollision matrix, and for this one what would be the eigenvalues and eigenvectors and eigenvalue decomposition, those things we'll be discussing. So let lambda are the eigenvalues and q. So if I consider one eigenvalue is lambda and corresponding eigenvector is q, then we understand that rq equals to lambda times q, right? Then we can take this one, the r minus lambda I, that is times q, will be equal to null vector. And to find these eigenvalues, we will put this r minus lambda I, its determinant, equal to 0, and then we will solve for lambda. So to do that, so this is the r, 1 r, r1, and this is your lambda I, lambda, this is 0, 0. If you simplify it, you will get 1 minus lambda, here also 1 minus lambda, this will remain r, This determinant we can find out. So its value will be this 2 multiply minus this 2 multiply, and that will be equals to 0. So this term, first term, this is 1 minus lambda whole square minus r square, that is equals to 0. So we'll have two factors, 1 minus lambda plus r, 1 minus lambda minus r, that is 0. So lambda will have two values. From this one we'll get lambda equals to 1 plus r, and from this one lambda will get 1 minus r. So these two are distinct eigenvalues. Now here you see with r equal to 0, both the eigenvalue will become same. That is for white input sequence, right? So we have got two different eigenvalues. One is 1 plus r, other one is 1 minus r. Okay, but what are the corresponding eigenvectors? Now if I consider first the eigenvalue equals to 1 plus r, that I'll call it lambda 1. And for this lambda 1, suppose q1 is the corresponding eigenvector, and this value, this vector is 2 by 2, so 2 cross 1 vectors. Okay, so this element, suppose it is q10, it is q11. Okay, so this is your q1 vector. So with this R matrix, if I multiply this q1, I'll get same lambda 1 times q1. So you remember, this is your lambda 1, 1 plus r, and this is your q1. Okay, now first equation what we'll get, 1 times q10 and r times q11, this two addition will be equals to 1 plus r times q10. Similarly we'll get second equation. So you see These are the two equations we will get. Okay, and from these two equations we'll try to find out the eigenvectors. Now these two equations will give you the same result. If you simplify it, so this q10 will cancel, then r times q10, this left side r times q11, that means q10 equals to q11. Okay, or q11 equal to q10, same thing. Here also you will get same result, because here r q11 will left right side, and q11 here and q11 here will cancel, so this r q10 equals to r q11, so r will cancel, so q10 equals to q11. That implies that these two elements are same, so ratios are same. Okay, they are exactly same, so ratio is 1. Okay, so I can put it is 1 1 for simplicity. So q1 I can start with 1 1, right? So if I consider this 1 1 element, both are same, then the norm, the L2 norm of this one will be square root of 1 square plus 1 square, that is your 2, square root of 2. So it is not unit norm. So to get unit norm, we have to divide by this norm. Okay, so we may consider q1 as 1 upon square root 2, again 1 upon square root 2, and this vector will have unit norm. In the same way, we'll go for lambda 2, that is 1 minus r. So for that, we'll consider q2 is the corresponding eigenvector, and elements are q2 0, q2 1. And so you understand this matrix R multiplied by this q2 will be 1 minus r times q2. So again, we'll get two equations, similar equations, but here you will see we'll get something opposite. So similar, but here q2 1 will be minus of q2 0. So one is opposite of others. From both, the same thing will get it. Okay, so here if I consider this is 1, this should be considered as minus 1. So q2 I will consider 1 and minus 1, and its norm again root 2. So we can consider q2 in this way, 1 upon square root 2 minus 1 upon square root 2, that will give you unit norm. Okay, so for this autocorrelation matrix R, where this is 1 1 and this is r, we have two different eigenvalues, that's 1 plus r and 1 minus r, and you see r is within plus 1 to minus 1 always, thus eigenvalues are always positive. Okay, and these are the corresponding eigenvectors, and you see these two eigenvectors, if you take dot product, it will be always 0. Okay, and now we can make this q matrix, that is this q1 I'll put first and then q2 in the second column. So this first column is this one, 1 upon root 2, 1 upon root 2, and second q2, this one, 1 upon root 2 and minus 1 upon root 2 here. So 1 upon root 2 I can take common, it will become 1 1 1 minus 1, right? And I capital lambda will consider here lambda 1 lambda 2, and this is 0 0 diagonal matrix. Here in this case 1 plus r, it is 1 minus r, it is 0 0. So you see, if I use eigenvalue decomposition, then R could be considered as Q capital lambda Q transpose. So Q means 1 upon root 2, 1, 1, 1 minus 1. That is your Q, already I have considered. Okay, this one. And this is your capital lambda. And it transpose. So they again same factor, 1 upon root 2. And this will become same. Okay. In this case, it is exactly same, symmetrical. Right. Now, we want to show that this product is exactly giving you this matrix 1R R1. Let us see. We will verify this one. So first, this 1 upon root 2, 1 upon root 2, I'll multiply and it will give you 1 upon 2, and these two I can multiply 1 plus r 0 0 1 minus r with 1 1 1 minus 1, then what will get 1 plus r times 1, and 0 times 1 is 0, so here it is 1 plus r. The next one is 1 plus r times 1, and 0 times minus 1 is again 1 plus r. Similarly, this one, it is 0 times 1 and 1 minus r times 1, that means 1 minus r, and here minus sign, that is careful, 0 and minus of 1 minus r means minus 1 plus r. So again you can multiply these two, then what will get? So if you see, if you add these two, so the 1 multiply this one, 1 multiply this one, then add, so r cancel out, it is 2. So first term is 2, and second term similarly this one, 1 will cancel out, plus minus 1 cancel out, so it is 2r. Similarly, you will get here 2r, here it is 2. So if I then divide by 2, you will get 1 1 r, exactly same this one. Okay, so we can verify this eigenvalue decomposition, right? And this concept, eigenvalue decomposition, this eigenvectors, eigenvalues, these are important concept in adaptive signal processing. We'll discuss this thing in detail in due courses, and I'll show you that the cost function that we have considered initially, there you'll see if it is 2 by 2 matrix of R, means only two weights W0 and W1, and for that the cost function, the quadratic equation you will get, so that will give you one elliptical surface, ellipse, right? And that ellipse nature, and you will see major axis and minor axis, actually these are given by these two vectors. Okay, that will prove in future courses, in future lectures. Okay, so keep watching all the lectures and you will find all the concept. And in the next video we'll discuss one important concept, that is gradient descent algorithm. I hope most of you are waiting for that. And nowadays machine learning is a hot topic, and in the next video I'll try to discuss the relation between adaptive signal processing and machine learning. I'll show you the similarity and the difference between these two techniques in detail. Okay, so keep watching my videos. I hope if you have not subscribed my channel, you are going to subscribe it. And to for subscription, you can first press the subscription button, and then don't forget to press the bell button, because then only you will get immediate notification for my future videos. I hope you are going to subscribe this channel. So thank you very much. Keep watching. Okay.